Thank you for organizing this great workshop. I'm going to talk about quantum computational unpredictability entropy and some applications. This is based on this talk I'll mostly focus on the CQ state that we developed in the first paper. I'll mention from the start, there's already follow-up work on the fully quantum variant of this entropy with two more co-authors, Joe and Thomas Hahn, that are here in the conference. I want to use this opportunity, this talk, to also invite you, if you're interested in computational information theory, computational entropies, to come talk to us, talk to me during the coffee break. I'm very interested. There's a lot more, I think, to do on this with this framework. Sorry. Okay. The structure of the talk, I'll first give some motivation. What do I mean by computational entropies and unpredictability entropies? I'll give the definition. We'll present some properties that we expect an entropy measure to have, that these entropies indeed have. Maybe the central information theoretic results here is that it has a good leakage chain rule. Should explain what it is. And it's the predictability entropy is a computational variant of the mean entropy. So I'll talk a little bit about extractors. We managed to show that you can extract pseudo-randomness out of these entropies. And I'll talk a little bit about the future directions that we are looking at. There's a lot, like I said before, there's a lot more to work on in this direction. Let's start with some motivation. What do we mean by computational? In the context of this talk, I want to talk about information processing under the assumption that the information processing happens in some finite time, which we measure by, for example, quantum gates in a circuit. So if we're interested in a one-shot setting, we can look more concretely on a one-shot setting where the processing is also efficient. So it will actually get the processing done in a finite amount of time. Any machine that runs in that we're restricted to running in finite time, there will be information processing tasks that it will not be able to do. This, if you're familiar, we mentioned before P versus NP. This separation comes before this NP assumption. It's simply for a counting argument. So it's not conditional that there is a gap between the computational and information theoretic setting. This counting argument holds just as well for the quantum setting. There's simply more information processing tasks that will be circuits of any size. And we're interested in talking about the uncertainty that's associated with this computational hardness. So to give a concrete example, something to keep in mind in this talk, if f is a function that it's possible to invert, maybe, but it will be computationally hard, what should we assign to the entropy of x given f of x? So it will be hard to guess x, but maybe it's possible to guess X. So the mean entropy will be 0, but we are interested in the entropy in the case that the guessing circuit will be computationally limited. Some more motivation. This subject has a very rich and developed classical theory. There's a lot of cryptography that uses computational entropies. There's a lot of results in computer science, even beyond cryptography, related to de-randomization, to pseudo-randomness in to pseudo-randomness, to even graph theory and complexity-related results. In addition, things more related to this talk, they have good established well-behaving chain rules. It's known that you can extract with randomness out of those entropies. They're related to leakage resistant cryptography. And the theory is very well developed. I want to focus on this talk on two main ways to define this notion of computational entropy. One is basically to take the smooth mean entropy and replace the smoothing with computational indistinguishability. So instead of allowing for some statistical variance in the state we're looking at, we'll allow for some computational variance in the state we're looking at. This has been done by another group. This has been defined here in the classical world in 2007, and in the classical world, it's pretty well behaved. And the second notion is the unpredictability entropy, which is what we'll focus on this talk, where we directly bound the computational complexity of the guessing circuit. Okay, this is in the classical world. Sorry, I said 7. This is the seminal work, the Hill entropies from earlier, showing that you can get pseudo-randomness for any one-way function, which is perhaps something to keep in mind in this talk. In the quantum setting, however, there is much less theory. There has been one paper until pretty recently trying to do that, defining the quantum Hill entropy, like I said, by doing computational smoothing. However, it lacked some basic properties we would expect from computational mean entropy. For example, the leakage chain rule that I'll present soon is only valid in the CCQ case, that only the new leakage is quantum and all the prior information and the secret are classical. This work will be defining quantum unpredictability entropy by extending the guessing probability with classical side information to quantum side information. And there is worth mentioning some recent developments in this direction, working on from the complexity constrained thermodynamics direction. It seems that it's not directly comparable to any of those works, but perhaps another avenue to think about. Okay, let's define let's officially define how we do this unpredictability entropy. The mean entropy, we know that for a CQ state can be defined as the negative log of the probability of guessing X given some side information. However, this includes guessing strategies that are computationally inefficient as well as computationally efficient. So we can simply restrict the guessing strategies to a circuit of size S. Usually when people define complexity and efficiency, it's a common practice to treat all polynomial time machines as the same. Here we're a little bit more refined. We actually count the gates, but if you think of this as a class of polynomial time machines, all the results here will hold just the same because all the reduction when we actually count the gates turned out to be a polynomial time. We also introduced a smooth variant of this, which is directly comparable to the smooth mean entropy. Here's the full definition of the smooth variant. We define it by using the purified distance. So we allow for statistical indistinguishability and not computational indistinguishability, like maybe you might expect. This turned out to be like a key difference that we need in order to for the leakage chain rule and the other results to hold in the computational setting. This was a drawback of the Hill quantum pseudoentropy. Some properties that we expect this to have, and it indeed has, immediately we can see there's a gap between the mean entropy and the unpredictability entropy for any S. We can find if we have a function that has an inverse, but it's hard to invert, like we expect, the unpredictability entropy will be high while the mean entropy will be 0. It's lower bounded by the smooth mean entropy because the operational definition of the mean entropy is by all circuits, and here we restricted the set of circuits. And we recover the mean entropy if we allow the computational power to be unbounded. We also have a data processing inequality. You might think, I just told you there are states that if you process the data enough, you'll be able to guess. So indeed, we don't get the data processing inequality with the node modification. We have to pay for the gates that the data processing channel consumed. The idea here is basically that the best thing the guessing addressee can hope for is for the data processing channel that we're talking about will be exactly what it wanted to do for the optimal guessing strategy. This is what will, this is the thing that will optimally increase the guessing probability after the data processing. But if we pay for we reduce the number of gates accordingly, we recover data processing inequality. We also see that it's monotone both in the circuit size, which is also should be intuitive that if we allow for more strategies, we can only guess better. And like the smooth mean entropy in the smoothing parameter, if we allow for more states, we can only improve. Now for main theorem of the paper that we have the leakage chain rule. What do I mean by a leakage chain rule? I have some tripartite state, and that's classical on this side and quantum on the side information registers. And I want to bound the difference between knowing a few more qubits and not knowing a few more qubits. And what we'd expect is exactly that 2 more qubits will hold 4 more will let us improve the guess by 4 more bits of information. The 2 is here for super dense coding. The difference in circuit size is bounded by the circuits, but the size of the circuits that's needed to generate the maximally missed states on these L qubits. Perhaps giving you some hint on the proof that I'm about to show. Again, this is a result that does not work. This is a result that does not work in the Hill setting beyond only CCQ states, meaning only C can be a quantum, and the proof is much more complicated in the Hill case. Let's see the full proof in 2 slides, starting with a slightly easier case of classical distributions. Here in classical distribution, we don't have the 2 because we can't do superdense coding. And the idea is very straightforward. There is an optimal guessing circuit that gets all the side information and gets with some probability. If we don't have this Z additional register, we draw at random. There is some good input. Will be like a correct input that the circuit expects to get. So the probability of guessing correctly can only reduce by 2 to the L, because at least one input will be good. Now we can extend this to the quantum setting by simply replacing the probability inequality of there exists one correct input by this pinching inequality, and the circuit will do exactly the same thing. It will generate a maximally mixed state on those extra qubits and run the same guessing POVM. And we see that because of this pinching inequality, the 2 that we expect to have from superdense coding emerges in the proof. Worth mentioning that I didn't define it, but the fully quantum variant of this unpredictability entropy is also has this chain rule exactly like you expect. So if X is quantum, and we define some notion of unpredictability for quantum states, this holds just as well. So it's valid even in the fully quantum setting. Okay. Now, if we want to also introduce smoothing, because most of these proofs were for the non-smooth variant, this is where we see that we need the purified distance, or at least some information theoretical distance. If we use maybe the trace distance, we will get some difference in the epsilon because of the Fuchs van de Graaff inequalities, but that will be not that terrible. But if we move to the computational distance for indistinguishability, everything breaks down. Here I'll explicitly say that we use the purified distance for this extension property, that the state that the smaller state that the guessing circuit gets should extend to a state with the C register without increasing the distance. So this doesn't really happen in the computational setting with computational smoothing if we allow for BNC to be quantum. Okay, this is the computational distance doesn't have this property, and this is why the Hill entropy doesn't have this nice chain rule beyond the classical quantum states. Now, for mean entropy, we'd want also to extract uniform randomness. If we have a sufficiently high mean entropy, we know that there are extractors that can use some public seed and extract shorter strings that are almost uniform random, even if the adversary knows the seed after the fact and holds some quantum side information. with from mean entropy, nearly uniform SID, and nearly uniform output. Okay, but we're here, we said the computational setting, we can't really hope for to get true randomness. Like we said, we can start with something with 0 mean entropy, but we can hope for something that computationally is indistinguishable from uniform randomness. For computational analysis, we call that pseudo-randomness. It's known that not all classical proofs for extractions extend to the quantum setting, and it turns out that even the proofs that work in general in the quantum setting, not all of them extend to this unpredictability entropy. For example, not all of them extend to the predictability entropy. For the Hill entropy, this part is actually rather easy because you basically replace anytime you say distance with computational distance, and proofs are easy to the Hill entropy. But for the entropy will require some more structure for the proof. The structure for the proof is that if what we want to have is a reduction that if I can efficiently distinguish the output from uniform randomness, I will also be able to efficiently predict the input. And some known results about quantum proof extractors do not necessarily have this property. For example, a classic, like a fairly well-established proof that only one bit extractor is quantum secure involves an inefficient guessing strategy based on the pretty good measurement. So this doesn't translate automatically to any two sources with unpredictability entropy. However, with the specific extractors, for example, the inner product extractor, we can do that. We can show security. This is the result if there's enough unpredictability entropy, namely 1 minus log 2 log the epsilon error. We can extract a bit of pseudo-randomness. And like I said before, there can be no mean entropy at all in the beginning. The seed has randomness, but it ends up being public. So we got something that behaves like uniform randomness, like a fair coin toss, if you're computationally bounded, from with no real entropy input at all from there is no true randomness in this process in the yep. Here's how we do it. Yeah, we basically if we have a guessing strategy for the output, we can translate it with such a circuit to a guessing strategy for the input. Okay, I'll wrap up. We introduced a new computational entropy based on guessing. We prove a leakage chain rule in the fully quantum setting. We show how we can extract pseudo-randomness from sources with enough unpredictability entropy. And we, in the paper, didn't really go into the talk, they talk about leakage resilient cryptography and models of quantum leakage from cryptographic protocols. Future work, I mentioned before that the key barrier for the Hill entropy is that there's no really computational variant of the purified distance, a computationally meaningful distance measure that has this nice property that if we extend, we don't increase the distance. We only showed it for inner product and extending the output less using Trevisan extractors, but there are a lot more extractors, short seed, multi-source extractors that are worth looking into, and we think, yeah, it's worth looking at. There's a lot of potential there. Going beyond just the CQ state, like I said, there's also already a follow-up work of some extension to fully quantum and to other computational tasks. We look at decoupling, data compression, and entanglement distillation, and beyond. Interesting to look at. There's a lot of open questions worth looking at the preprint in the archive. And many other entropies. Here we only focus on the mean entropy, with near entropies, the computational max entropy, other computational entropies. Will be related to other information processing tasks that are typically described by conditional entropies. Okay, that's the end of the talk. Thank you.
Okay, thank you for the talk. We have time for questions. Yeah, okay. Yeah, sure. I mean, I don't know if, well, for the recording, it's always good to have your voice completely.
Thanks for the talk. Do you know anything about an asymptotic equipartition property for this new entropy?
No.
Do you expect it to give back the usual min entropy, or?
So in general, in the asymptotics, it's a little delicate because you need to also extend the computational power in some way. So if the computational power is also asymptotic, then you recover the mean entropy. So you need to look at the rate where the computational power and the tensor product of the state go together.
Like it would depend on the scaling of the circuit size in a little bit, right?
Here we're like we fixed the circuit size, then talked about like the circuit size is fixed, and then we talk about states with the mean entropy with in relation to that circuit. But we can also do the other way, but we didn't yet.
Okay. Well, okay, I think everybody seems to be happy. Is there no one in the Zoom? No, today they're not very active. Okay, so then let's thank Noam for the talk. And we have a coffee break until 11:15. So.